As you know, we have been conducting these online talks since October 2023 with the main intention of informing our members and students about developments in various fields apart from what they normally studies. So these are mainly introductory talks which are given by teachers, faculty members from colleges and universities. And we have covered a variety of topics, all the way from cosmology to quarks. And we have also conducted a few talks in Kannada also. So our another one of the objectives is to introduce our faculty members and students to resource persons who are available in our area, so that if they want, they can pursue further studies or further discussions with them. That is also one of the objectives, is to gather physics faculty members, resource persons, and inform our students about their availability. And we have also conducted talks in Kannada with the objective of introducing Kannada in higher education. Maybe that should happen later on, but when it happens, we don't know. And this is the kind of activity we expect from every developed university or an academy, a science academy. If you take in developed countries, they have this kind of activities, outreach activities regularly. Unfortunately, they are not doing it, and we are filling in the gap. So we are providing that kind of a service to our teachers and students. So today I welcome our distinguished speaker, Dr. Vijay Sai from SSSIHL Sai Institute. He will speak about applications of nuclear radiations for about 15 minutes, followed by some question and answer session. So before I request him to speak, I request our Joint Secretary, Dr. Kiran, to please introduce the speaker briefly. Over to you, Kiran.
Yes, sir. Yes, sir. Yes. Good morning, one and all present here. It's my immense pleasure to introduce the Dr. Vijay Sai, the speaker of the day. He obtained his BSc honors in physics from SSSIHL Institute of Higher Learning in 2000. Continues his academic journey by obtaining master in physics with a specialization in nuclear physics in 2002, followed by a doctorate degree in 2007 from the same institution. And Dr. Vijay Sai joined the Department of Physics in 2007 and also obtained an authorized radiation safety officer, that is AERB, designated by SSSIHL Institute of Higher Learning. His proficiency in nuclear spectroscopy is evident from the peer-reviewed journal articles about 120 national and international journals as he authored, engaging the activity in both research endeavors and development of course curriculum. Dr. Vijay Sai balances his responsibility along the side with full-time teaching commitments. And also he is a faculty in charge for the liquid nitrogen facility and functional material lab and facility at SSSIHL Institute of Higher Learning. And reviewer of this some of the reputed journals of IOP elsewhere and also international conference. And he is a member for the academic council member in the SSSIHL Institute of Higher Learning, chairman of Board of Studies, Department of Physics, one of the lead Vedam group member, a regular Vedam chanting in Prasanti Nilayam, participated in many Ekadasi Rudra Upanishats. And also research areas interest is nuclear structure and nuclear spectroscopy as well as electron gamma spectroscopy. And also novel electroceramic materials for energy storage application. Thank you for accepting our invitation, sir. Vijay Sai, sir, over to you.
Okay, please start.
Thank you, Dr. Kiran, for a brief introduction. Om Shri Guru Bhyo Namaha Harihi Om Om Sabhabhyas Sabhapatibhyascha Namaha. I offer my reverential salutations to Bhagwan Sri Sathya Sai Baba, our founder chancellor, Sri Sathya Sai Institute of Higher Learning, for shaping me and for who I am today. And my sincere gratitude to Professor Basavaraj, former professor and chairman, Physics Department, Bangalore University, Gnana Bharati campus, and Dr. Kiran, and also to Dr. Nanda, who had given my reference. Today, I am going to share with you all whatever little knowledge that I have about applications of nuclear radiations, from the invisible to the indispensable. It's a scientific journey with a holistic perspective. So, just before dwelling into the subject for today, one or two slides or say 2 3 minutes about my institution and university. The founder chancellor emphasized more on education is for life, not for mere living. And this institute has not been established just to prepare you for earning degrees. The main purpose is to help you cultivate self knowledge and self confidence so that each of the students that they study here can learn self sacrifice and earn self realization. These are very high uh, motivational things which our founder chancellor had emphasized more on. It's a educare, not education. It's a modern Gurukula, was founded to inculcate ethical and moral values in students. These ethics and morals form the undercurrent of every subject taught at the university. The sir, just a one or two sentences about this, and then I'll go into that.
No, no, please carry on. No problem. No problem, sir. Please.
The development of a student's character is just as important as imparting knowledge. This holistic development of students can only be possible in an environment that encourages the student development of the student's mind, body, and spirit. And to facilitate this, the university has a compulsory residential policy for all students. The environment is similar to ancient Indian Gurukula system of education in a modern context. Most of the teachers and students live and grow together in an atmosphere of mutual trust and unity. And most students here typically spend between 2 to 5 years pursuing an education. As a result, what differentiates them from graduates from other universities is the transformation of their hearts, not just the training of their minds. And the emphasis by the founder chancellor is the cultivation of human values alone is true education. So there's a very pictorial uh, administrative building and a Hillview Stadium that we have, and these are the four campuses which our university has. One in the Anantapur campus for entirely for women, and the other three campuses, one located in Whitefield and the Brindavan campus, and the other two, Nandagiri campus. There's also near to Mudanali. These are these are Prasanti Nilayam main campus in Puttaparthi. The Upanishadic verse, Anoraniyan Mahato Mahiyan, Atma Guhayam Nihitosya Jantoh. There's a very profound Upanishadic verse. The self is subtler than the subtlest and greater than the greatest. It resides hidden in the heart of every living being. This verse beautifully captures a profound idea. Ultimate reality is not constrained by size or scale, it pervades both microscopic and cosmic, yet remains intimately present within the human being. In a modern scientific context, it resonates with how fundamental laws govern both subatomic particles and the vast universe, while consciousness remains an inward experience. And also, there is one more Upanishadic verse that I would like to say before I start the topic. Ekam Sat Vipra Bahuda Vadanti. This verse expresses a profound epistemological idea. Reality is one and unified. Human understanding describes it through multiple names, models, and perspectives. In science, this parallels how a single physical reality is described using different frameworks like classical mechanics, quantum mechanics, relativity. Each are valid within its own domain. In Indian thought, knowledge is never seen as fragmented. The same reality is explored through different lenses like science, philosophy, and experience. The Upanishads remind us that truth is one, though expressed in many ways. In physics, we often study the invisible, like the forces, fields, particles, radiations, whose presence we infer only through their effects. Nuclear radiation is one such phenomena, unseen but powerful and transformative. So we'll be having a holistic beginning about how seeing the unseen, understanding the invisible. So much of nature's power is invisible to the human eye. As I mentioned, forces, fields, waves, particle radiation, all this we know only through their effects. Nuclear radiation is one such subtle but powerful phenomena. Science progresses by making the invisible visible, from ancient intuition to modern measurement. So, radioactivity, don't get scared by this word. And one more thing, one more disclaimer that I would like to make is it is very rudimentary or introductory talk. I'm not going to really go very deep into any of these concepts. Okay. So, what do we mean by nuclear radiation? Okay, it basically there are atoms, the nuclei inside it, which is the center or core of the atom, where most of its mass is present, like say the protons and neutrons which form the nuclei. And so the this nuclear radiation is emitted as particles, like say ionizing radiation or non-ionizing radiation. Particles like alpha particles, alpha particles or helium nuclei, basically beta particles, electrons, neutrons, and electromagnetic radiation, gamma rays. By this nuclear radiation, basically how they interact with matter and how they deposit energy, that's what we are more interested in. So the same radiation can have different applications depending on how we use it. And radiation by itself is neither good nor bad. It is our understanding and control that determines its role. Once we understand how nuclear radiation interacts with matter, we can begin to appreciate how it has been harnessed across medicine, industry, energy, environmental studies, agriculture. So there are many applications that nuclear radiations have found its use in. Um, uh, the slides are visible and my audio is clear, right,
Yeah,
sir?
yeah, very clear. Yeah, please proceed. Clear.
So interaction of nuclear radiation with matter. So this is one very center or key uh, topic that we need to understand. Like say, for example, if you take a gamma radiation, like how it interacts with matter is through these three processes, physical processes, like say photoelectric effect, Compton effect, and pair production. So if you take photoelectric effect, it is the full energy of the radiation is absorbed or deposited in the material. So the signal that we get correspond to the amount of energy the radiation has imparted in the material, right? So the nuclear radiation interacts with matter by these ionizing atoms and molecules, depositing energy in a controlled manner. So these interactions lead to measurable and predictable effects. Like say ionization, it creates detectable signals. Excitation, some kind of say in scintillators, there are scintillator materials. So again, it's a the whole branch in material science. You can look at a material which has got scintillation properties. Okay. So energy absorption, heating, damage, or transformation. So these are some of the interactions. What I mentioned earlier for gamma radiation, those are the three main processes: photoelectric, Compton, and pair production. So some of these key understandings of interaction of radiation with matter are being used in many applications with nuclear radiation. So every application of nuclear radiation is based on controlled interaction with matter. So applications are not about radiation itself, but about how matter responds to the radiation. So, for example, there are many natural sources, like say cosmic rays, environmental, if you take the atmospheric and terrestrial, say potassium 40, carbon 14, these are some of the natural sources that are there, which are the sources of radiation. And then the human body or the human tissues are exposed to that kind of radiation every second or every moment that you take. Even the banana that you take, that has also got some radioactivity, maybe in very minuscule activity, but it does have radioactivity. Okay, so other man-made radiation are, like say, in medical field, medical and dental, X-rays, radioisotopes, pharmaceuticals. All these are man-made radiation sources, and there are occupational exposure that is there from radium, uranium, and say nuclear fallouts, nuclear accidents, the exposure for many years. Chernobyl is one such example. TV, computer, mobile, all these are sources of man-made radiation. So if you see sources of radiation, medical X-rays, nuclear medicine, consumer products, terrestrial, cosmic. So all these are artificial radiation sources and natural radiation sources. Okay, and yeah, to speak little bit about the radiation, gammas, which we are mainly interested in, it's a radioactive element emitting gamma rays, photons. So they have no mass or charge. They create ionization events needed for sterilization, have very short wavelengths. So the in the electromagnetic spectrum, if you see X-rays and gammas, those comes towards the shorter wavelength region where they have very high energy. So that energy can be used or in medical applications or many applications. We'll be seeing it in the further course of the talk. So they can penetrate, since they are very energetic. They can penetrate deeply into any product or in human tissue. Okay, and then cause mutations that might help curing, or that might damage. So it is both ways it is used. Okay. So it makes them as an excellent sterilizing agent. Some of the very standard gamma sources are cesium 137, cobalt 60. So cesium 137, if you take, it is a monoenergetic source, like say 660 keV of energy photons that are emitted from cesium 137. When cesium 137 is decaying by beta minus decay, okay, um, so there are negative beta decay or electron capture. There are many ways that a nuclei can decay to become stable, right? And also, like say, if it is excited, the de-excitation happens through emission of gamma rays, and this gamma rays has nothing but energy. So as I mentioned, cesium 137, it is a monoenergetic source which is emitting 660 keV gamma photon. Okay, so that is used mainly for calibration purposes. So for example, somebody is working in nuclear spectroscopy, so that is the first isotope or first radioactive radioisotope that they use to see whether they get a proper 660 keV peak or not. Based on that, you can calibrate the entire spectrum. So, and it has got many industrial practices, industrial applications as well. Okay, so this is all I mentioned about the gamma rays. And when you talk about this gamma radiation, there are three things that we need to keep in mind. Not only gamma radiation, but for any nuclear radiation as such, there is something called TDS. Most of you who are getting salary, you know what is TDS. But in this particular nuclear parlance, TDS refers to time, distance, and shielding. The amount of time that you spend near a radioactive material or radioactive isotope, that you should minimize. So whenever you are doing some experiment or using the isotope or radioactive material for some application, use it, and then you have to keep back safely in the shielding. So the TDS, the S is for shielding materials. So for example, this gamma rays, if you take lead, which is very heavy, it's toxic also, but it is very heavy. So that can stop the gamma radiation or shield the gamma radiation. It can attenuate. Okay, so there are again so many calculators which you can use it to say how much amount of thickness of lead is required to stop a gamma radiation of some particular energy. Okay, and for example, if you take neutrons, you need hydrogenous material or boron kind of material which can stop the neutrons. So for different radiations, different materials are used as shielding, because you need that kind of shielding from these radiation, because they can interact with human tissues and then cause damage. And they travel with the speed of light, at the speed of light. Okay, so here there are few, say cobalt 60 is one more very standard gamma source. Cobalt 59, which is stable when it interacts with a neutron, when it is interacting with it, it can produce cobalt 60, which is unstable, which gives rise to gamma rays of 1.17 and 1.33 MeV gamma rays. Cobalt 60 has a half-life of about 5.27 years, and the cesium 137, what I spoke about, it has got a half-life of about 30 years. Half-life, I think most of you who have studied a little bit of nuclear physics will understand that, say, a cesium 137, if you take a source, it reduces to half of its activity by that much amount of time. And the beginning of this is in around 1900, 1895, 1900, around that time, started with radioactivity by Henry Becquerel. Okay, then the X-rays, Rontgen. X-rays was a little before. So it's nuclear physics as such is not really that old physics compared to most of the physics branches, but it has found many applications over the years, and the developments that has taken place. Okay, so in medical field mainly, it has got its application very much. Okay, yeah. So from interaction to applications, one physics, many applications. So these are some of the domains that I mentioned here: medicine, industry, energy, environment. In medicine, imaging organ function, destroying cancer cells. Say in industry, there is something called NDT, non-destructive testing. It's a thickness and level control. In energy, nuclear fission, um, heat, electricity, and environment, tracing the pollutants, dating geological samples. These are very brief overview of in which all domains and how it is being used. same radiation, but the different. In India, if you take Department of Atomic Energy, DIE, that is the most um, the one government agency where work or research that is done in nuclear physics, material science, atomic physics, and so on. I'll come to those details also later. Um, so nuclear radiation quietly supports society, often unnoticed, but yet indispensable. So let me now briefly illustrate how these principles manifest in each of these domains, beginning with nuclear medicine. As I mentioned, in radiation applications, it has got applications in health, energy, environment, and climate change industry, in all these branches or fields. Medical uses of radioactive materials and radiation. So this symbol that you find here, caution radiation area. So if you see in photonics or optics, laser source, I can see very clearly, or you should be able to distinguish that there is a laser source. We should be very careful with it. Unlike the lasers, this particular radiation, it is not visible to eye, naked eye, and you'll not be able to know whether it is present or not also. There are something like Geiger counters. That is a simple experiment any undergrad student would have worked or would have seen, right? So this is Geiger counters which can count whether any radiation is present or not. It may not give you an idea about what kind of radiation or what kind of energy that is present, but it just says that a radiation is present, so be careful. Okay, so in nuclear medicine, the radioisotopes that I was mentioning, I think by now you all know what is an isotope, right? It is a nuclide with same proton number. So carbon 13, carbon 14, carbon 15, so oxygen 16, oxygen 18. So many are there. For each nuclide, there are many isotopes that are possible. And radiopharmaceuticals are some of the radioisotopes. Uh, and anyway, later I'll be coming to the DA institutions, BARC. Most of you would have heard about Baba Atomic Research Center, and there are some divisions in it. There is one thing called BRIT, Board of Radiation and Isotope, which um, say make these radioisotopes or radiopharmaceuticals for hospitals and many centers. Okay, so diagnosis is one and treatment is another. So nuclear medicine, the nuclear radiation through this nuclear medicine, it is applicable both for diagnostic and treatment purposes. So what is nuclear medicine used for? Will I be radioactive after nuclear medicine scan? Or how does nuclear medicine work? Are nuclear medicine tests safe? Why someone might need a nuclear medicine scan? So
Want
some
to
of
spend
these,
some time with him.
hello.
Please
Yeah, some
carry
of
on.
these questions I'll be answering while during this talk. So nuclear medicine is basically it's a specialized branch of medicine that uses radioactive substances known as radiopharmaceuticals for both diagnostic and treatment of diseases. And radiopharmaceuticals, these are radioactive compounds that are introduced into the patient's body through swallowing, injection, or inhalation. Depends on which scan which you want to, which is medically relevant. Okay, based on that, this radiopharmaceutical or radioactive compound is introduced into the patient's body, and it has got targeted distribution in the body, meaning that, say, some of the radiopharmaceuticals or radioactive compounds will have affinity towards some organs in the body, like say iodine 131. Salt has got some kind of iodine. So this thyroid has got some affinity to this kind of iodine 131 that is being injected or introduced into the patient's body. So it goes to that particular organ, and then it starts emitting radiation from there. So because of which he'll be able to take an image of how the or know the functionality of that particular organ. Okay, so there's a targeted distribution in the body. Once administered, these substances accumulate in specific organs or bones or tissues, depending on their biochemical properties. So, as the radiopharmaceutical travels through the body, it emits radiation, which is detected by specialized imaging systems such as gamma camera or PET scanners. PET, you might have seen PET MRI. So, PET is positron emission tomography. And there is a slight difference between nuclear medicine and radiology. Nuclear medicine can be described as radiology done inside out, meaning the radiation originates from within the body, unlike X rays or CT scans, where radiations come from an external source. There is an X ray source or a source that is reason for the CT scans that you take. Whereas nuclear medicine, it is a because of the radiation that is originating from within the body. The radiopharmaceutical or the compound is injected inside the body, and from there the radiation is emitted and being imaged. Okay, so that's a very actually a big difference in nuclear medicine and radiology. Radiology, the sources are external sources. Okay, so functional imaging. A key feature of this nuclear medicine is that it images organ function and physiology rather than just an anatomical structure. It is used to assess the function of organs such as heart, lungs, kidney, bones, and to monitor cancer activity. At this point, maybe I'll just mention about very briefly about the research that is done at Department of Physics SSSIHL, where indigenously we had developed, designed and developed a gamma camera, which is actually we labeled it as SAI-GC, small area imaging gamma camera. So for an organ like thyroid, you will not require a huge. Actually, the gamma camera nuclear medicine department in any hospital, the gamma camera, if you see, it occupies a quite a big space. Okay, but just for imaging a thyroid or a small organ, you don't require such a big system. So we had designed this small area imaging gamma camera, which can image or can assess the functionality of an organ. Okay, so the nuclear medicine procedures are very safe, with radiation doses comparable to diagnostic X-ray or CT scans. So radioactivity, when I talk about, the first thing that they talk about, the unit is becquerel. It is 1 disintegration per second. Okay, and then the higher activity is curie. So say something like 10 power 10 disintegrations per second, that kind of big number. So a curie of activity is quite dangerous. uh, okay, so the early detection of disease, because it detects molecular and functional changes, nuclear medicine can identify diseases at very early stages, often before the structural abnormalities appear. Okay, so the radiopharmaceutical is administered into the human body, as I mentioned, through inhalation or say as a through orally or through injection. Okay, so for example, I mentioned about say technetium 99 M, the metastable state of technetium 99 is a very common radiopharmaceutical that is used for heart-related imaging, myocardial perfusion, and so the functionality of an organ is one important thing that is nuclear medicine. So, say cancer monitoring, the performance of the heart, lung, kidneys, bones. So, all these are possible through this nuclear radiation, through nuclear medicine. So, it is both diagnostic as well as treatment. So, cancer treatment and also pain relief. Okay, so just a simple comparison of chest X-ray. These are some of the units that are used: sievert or millisievert. 0.1 millisievert is the dose rate. That is, if you take a chest X-ray, that is the kind of dose that is received through the radiation. Nuclear medicine thyroid scan, again similar 0.1 millisievert. Abdominal CT scan, if you take 10 millisievert. Nuclear cardiac diagnostic test, it will be about 10 millisievert. So these are the kind of doses that are being exposed, or the human body is exposed to when you take such a nuclear medicine test. These are quite safe, like say, as I said, for chest X-ray or CT scan that you take. So all these are well below the prescribed doses that a body can receive over a period of time. Okay, so nuclear radiations have various applications. The whole thing that I was mentioning most of the time is about nuclear medicine, cancer treatment, radiotherapy it is called, and then the diagnostic imaging through PET scans, X-rays, and sterilization equipment. All these are some of the applications in medicine. So there are other areas where nuclear radiation has found its applications. Say in industry, food irradiation is one very huge industry that so for food preservation, it is irradiation through nuclear radiation, and sterilization of products, cosmetics, pharmaceuticals, and radiation processing. Okay. And in agriculture, say for crop mutation breeding and sprout inhibition, in food for food preservation and so on. And for energy, you all know nuclear power generation. Uh, there are something called small modular reactors that are coming up. The research has done so much on those, and it's a greener energy and cleaner energy. Only thing is you need to take care of uh, the proper radiation shielding, and those things we need to take care of. Okay, and then research. There is so much research that is done in nuclear physics and in material science. Read how radiation affects the materials. Okay, even in our department also we do research in this particular domain on how radiation affects or different radiation shielding materials. I mentioned something about lead, which is very heavy and toxic, but that is being used in most of the medical domains, medical areas where they use nuclear radiation, right? So instead of a very heavy material like lead, we can have some other material with similar properties which can attenuate the radiation. So that will be very helpful to medical community. Like say the physicians, they may be using lead aprons which are very heavy while doing any um, medical say treatment or so, right? So for that, this kind of research in radiation shielding materials will be very helpful. Okay, and in security also, the nuclear radiations are used, radiation detection in like say even in airports also there are some mini scanners that are used using this particular nuclear radiation applications. Um, yeah, so in diagnostic imaging, X-rays, I said CT scan, all this, right? So nuclear medicine scans like bone scans, thyroid scans, these are all diagnostic imaging modalities. And yeah, radio tracers for studying disease mechanisms and development of new cancer therapies or targeted radionuclide therapy. Okay, and radiation therapy for cancer, high energy radiation kills cancer cells or slows their growth. And PET scans, they use radioactive tracers to image metabolic processes in the body, helping diagnose diseases like cancer and Alzheimer's. And if you see, it has got, the nuclear medicine has got its application in oncology, cardiology, neurology, say pulmonology, that is basically with lung related, and also pediatrics. This I had shown it earlier, talked about it, different kinds of radiations. So these pharmaceuticals, these are drugs that use radionuclides for diagnostics and as well as for therapeutics. These drugs are comprised of radionuclide attached to a targeting molecule that can be used to diagnose, treat, or monitor different diseases. So if you see these gamma rays, they travel much faster and then can penetrate deeper. They can be detected using specialized cameras. The one such as I mentioned is about gamma camera. There's a nuclear medicine imaging modality. They cause very little damage, very little when used with proper activity. Activity is one more thing that I would have missed out mentioning. So there is something called specific activity. These many millicurie or these many curie. Curie, as I mentioned, it is very high activity. So most of the research institutions or even the medical fraternity, they may not be using so much of activity, and basically it has to administer into the body, right? So for example, if you take technetium 99, okay, so it has got a half life of few hours or one day or so. So once the imaging or the diagnostic procedure is done, it will be excreted from the body. Okay, so it will not be staying within the body. So since the half life is quite short, so it will be emitted or ejected out from the body, and it is quite safe. That's what I want to say. So imaging and diagnosis, nuclear medicine diagnostics or molecular imaging uses radiopharmaceuticals to see how the body is functioning and to observe its chemical and biological processes. Other diagnostic imaging procedures, such as X-rays or computed tomography, assist in detecting changes in the physical structures. That's what I mentioned earlier too. The difference between, say, nuclear medicine and radiology. nuclear medicine, it can be used as treatment for many diseases such as certain type of cancer. In therapy, a radiopharmaceutical is injected into a patient's bloodstream where it binds to a specific receptor expressed on a particular tumor cell. Okay, so again, this particular slide I had mentioned about common radiology exams, whereas nuclear imaging exams. Okay, so this is a gamma camera. As I mentioned, it's a big machine. It occupies quite a big space. This is used to take a picture and obtain a projection image. It obtains a projection image of the patient, a particular organ that we try to see the functionality. It is also called SPECT, single photon emission computed tomography. So imaging of a patient on SPECT CT. So there are dual modalities that are recently developed with the technology. So SPECT is a gamma camera or a nuclear medicine imaging clubbed with it's a dual with CT scanner also. So it can give a better understanding of how the organ is functioning. Okay. So again, this I mentioned earlier, the radio tracer is injected into a vein, emits gamma radiation as it decays. Gamma camera scan the radiation area and creates an image. Okay. This is MRI, clinical magnetic resonance imaging. This is an imaging technique used in radiology to form pictures of anatomy and the physiological process of the body in both health and disease. Right? This provides clear picture of the structures inside the body. So application of nuclear radiation. So this is again a PET scanner. This uses radiation to provide an image of how part of a patient's body functions. So for this PET, again, there is so much of physics again background to it. Like say, a cyclotron, which produces that kind of main source that is used in PET is fluorine 18 based FDG. It is called fluorodeoxyglucose. So glucose is akin to the body, right? So when this kind of fluorine 18 FDG is injected into the body, so you can assess the functionality of a brain or any other organ. Right? The scan it produces can be used to image a healthy brain or can be used for diagnosing medical conditions such as Alzheimer's disease. Right? So this is one more for thyroid uptake system. So the functionality or assessing the thyroid, it can be used. But the one that we had made, I mentioned, gamma camera, it gives a much better understanding of the thyroid. So here is a comprehensive list of field-oriented list of radioisotopes used in medicine, grouped by diagnostic, therapeutic, and theranostic applications, like say SPECT, single photon emission computed tomography, or the gamma camera that is used. Technetium 99 M stands for the metastable state. Okay, so the work, which is the main workhorse of nuclear medicine, iodine 123, iodine 131, those are for mainly thyroid imaging and diagnostics in thyroid. Thallium 201, it is for heart myocardial perfusion. Gallium 67, again for lymphoma. Indium 111 for leukocyte and antibody leveling, lung ventilation. So yeah, these are a list of diagnostic radioisotopes which are used in different nuclear medicine modalities, like say SPECT. And then other one is for PET, positron emission tomography imaging, FDG, F18 that I mentioned. That is the main, again, workhorse for PET. And as I mentioned, all these radio compounds or radioisotopes that are injected into the body, those have got very short half-life. So those are excreted out of the body within a few hours or maximum a day or two. So if you are imaged after say 2-3 days or so, you will not be no radioactive trace is found in the body. Okay, so these are some therapeutic radioisotopes. Some are beta emitters, like iodine 131 that I mentioned, both for thyroid cancer and hypothyroidism, and lutetium 177 It is mainly for neuroendocrine tumors, prostate cancer, and so some of these isotopes we did work with those. And the one I mentioned about BRIT, Board of Radiation and Isotope Technology, that supplies to institutions and medical, say, hospitals where these kind of facilities that are available, and to institutions also where there is a uh, AERB approved radioisotope laboratory. Mainly, you need to have proper shielding mechanisms in the lab because you are handling radioactive material. Though it is of very low activity, you need to shield them well. The TDS that I talked about, time, distance, and shielding, you should have a proper shielding for the radiation that you handle, and the amount of time that you spend, and also the D is for the distance. Distance, like say a radioactive source that is at a 1 meter distance, it can cause less uh, harm than a radioactive source which is at a, say, half a kilometer distance. Okay, so the time, distance, and shielding, these are the three key words when you are working with nuclear radiation. So there are other alpha emitters, Auger electron emitters, which are used in therapeutic diagnostics and therapeutic radioisotopes. These are theranostic isopairs, so iodine 123, iodine 131 for thyroid, and say scandium 44, 47. And then there are some non-imaging medical uses also, like say iron 59, which is used for iron metabolism, and tritium, which is used for biomedical research, carbon 14 for metabolic tracing. Uh, then carbon dating is one more, which is not of medical usage, but later on I'll talk something about it. So brachytherapy, these are some of the isotopes or radiopharmaceuticals that are used. So the last one that I mentioned about most widely used are this technetium 99, F18, iodine 131, lutetium 177, so thallium 201. These are all some of the most widely used radiopharmaceuticals or radioisotopes in nuclear medicine. Again, you see here I have mentioned about top 15 radioisotopes used in medicine, and you see the half lives. Technetium 99M that I talked about, it has got 6 hours half life, which is used primarily in SPECT imaging for bone, heart, kidney, and so on. And F18, it has got 109.8 minutes, 110 minutes or so. That is roughly 2 hours. It's a beta plus emitter, and it is used for PET imaging and in oncology purposes. Just let me know, are you following, or is my audio?
We are following, yes.
Yes, sir. Thank you. So yeah, so these are all the top 15 radioisotopes that are used in medicine. So in diagnostic isotopes, they are short half-life, as you can see. These are gamma or beta plus emitters, whereas for therapeutic isotopes, these are beta minus or alpha emitters. And theranostics, there's the same element used for both imaging and therapy, like say gallium 68 and lutetium 177. Those are the isotopes which are used both for imaging and therapy as well. And you see, technetium 99M and F18, those dominate the nuclear medicine um, field. So, till now, I have spoken or talked about the nuclear radiation applications in nuclear medicine. In industry, nuclear radiations are used in various ways. Food irradiation, they extend shelf life by killing bacteria and preserves food without chemicals or heat. Used for spices, fruits, veggies, and meat. And sterilization, medical equipment, syringes, implants, all this for sterilization, this nuclear radiation is used. And in pharmaceuticals and cosmetics, packaging materials, nuclear radiations find their use. And non-destructive testing I mentioned, like say X-ray and gamma ray imaging for inspecting welds, pipes, etc., and also detecting flaws or blockages. This non-destructive testing through nuclear radiation, it is quite effective. And also in thickness gauges, that is measuring thickness of materials, controlling production process. Okay, sterilization is efficient. Um, Radiation can penetrate packaging, making it ideal for pre-packaged products and in food safety as well. In agricultural uh, domain, the crop mutation breeding and food preservation, pest control, soil and water management, these are some of the areas where in agriculture the nuclear radiations have got application. Okay? And in energy field, nuclear power generation, nuclear fission reactions, they produce heat. So that heat is generates steam and driving the turbines used in nuclear power plants worldwide. Um, the picture of reactors in BRC that you see, those are for say nuclear power plants, which are very useful and useful for the nation. So there are different kinds of reactors again: pressurized water reactors, boiling water reactors, heavy water reactors. Okay, so low greenhouse gas emissions during operation, high energy density, reliable power source. These are some of the advantages. Only thing is the challenges are the nuclear waste management. So there are courses from DRC or AERB. AERB is Atomic Energy Regulatory Board, which regulates the supply or issuance of, like, say somebody wants to do research, they need to take permissions from AERB to procure and handle radioactive sources. So it's not that Brit can supply to anybody who asks for these radioisotopes, right? So the it is radiation. It is dangerous if it is not used in a proper way. Yeah, this is the latest research is in SMRs, that is small modular reactors, which are quite safe and efficient. So in security field, in the field of security, nuclear radiations are used for detection and prevention. So detecting radioactive materials at borders or ports, identify nuclear threats or smuggling, used in security scanners and detectors, monitoring nuclear materials like uranium, plutonium, okay, and then explosive detection. Like, say, one of the common things that is used in buildings or areas, the smoke detectors, they use americium 241 uh, radioisotope that is used for smoke detection. So yeah, smoke alarms that I talked about for treating cancer, traces in medicine, tracers in geology. Okay, so these are some of the uses. And then radiation in daily life that I mentioned about, banana also has got some radioactivity, right? So these are some of the most common things that in our daily life they do have radioactivity, or they are some form of nuclear radiation. And this is a, on the right side, the image that I show is of yearly dose of radiation absorbed per person. So from cosmic rays, zero point 0.4 millisievert or so as a nuclear radiation, and from earth, even the soil or the hill rock, all that also will be emitting some kind of nuclear radiation. Okay. Radiation exposure in daily life. So what is the kind of I mentioned about units, right? Millisievert or microsievert. So constant of biological effects radiation into, again there is one more unit that is mentioned as gray, that is sievert. So AERB and then the regulatory bodies, they specify that this is the amount of radiation that a human body can be exposed to in a year. Even the flight air travel also has got some kind of nuclear radiation that which body is exposed to. In non-medical radioisotopes, these are the applications that they have. In industrial applications, in non-destructive testing, gauging and calibration, cobalt 60, iridium 192, cesium 137. So these are all the isotopes which are non-medical application, have got non-medical application. EU 152, it has got a wide range of gamma energies. So gamma ray energy calibration, EU 152 is used. And I mentioned about cesium 137, which is monoenergetic. That is also used as a calibration for detectors. Okay. And then nuclear power and reactive technology, uranium 235, uranium 238. There is something called fissile material and fertile material. Okay. In reactor fuel, neutron sources for reactor startup. So americium 241, which I mentioned for smoke detectors, right? That has got, again, if it is in a high activity, these are neutron sources which are used in nuclear power plants and also for monitoring. And some of the isotopes that you see here, those appear in multiple categories. which highlight that they are interdisciplinary importance. And then there are applications of the nuclear radiation or isotopes in space and remote power applications, like say radioisotope thermoelectric generators, the RTGs, those are called, and fusion research. Tritium is used in fusion research, self-powered devices, and it has got applications in geology and earth sciences as well. Radiocarbon dating, C14 or C14 dating, it is called, to find the say uh, the lifetime of that particular. Even for paintings, also this radiocarbon dating is used. Potassium argon dating, uranium lead dating. So yeah, environmental and earth monitoring. So these are some of the list of isotopes which are used in non-medical applications. And I was mentioning about Department of Atomic Energy. Sorry for the image is not very clear, but there are many uh, organizations or centers which are funded by Department of Atomic Energy. Like BRC is the main one, and then there is Tata Institute of Fundamental Research, Atomic Energy Commission, again AEC, that governs the whole of these institutions. And there are many national facilities and centers. Like say here I mentioned about research and development sector, BRC, IGCAR Kalpakam, Indira Gandhi Center for Atomic Research, Raja Ramana Center for Advanced Technology Indore, Variable Energy Cyclotron Center Calcutta. So these are some of the institutions where there is so much of research that is done towards societal applications. And yeah, these are some of the aided institutions: Tata Institute of Fundamental Research, Tata Memorial Center, Saha Institute of Nuclear Physics, Institute of Physics Bhubaneswar, Institute of Plasma Research Gandhinagar. So all these are aided institutions of Department of Atomic Energy, where there is so much of research work that is done. Just maybe few more minutes, and then I will wind up later. Can so as I mentioned, yeah, these are all the some of the major accelerator facilities in India. So accelerators and reactors, those form the eyes of nuclear physics or nuclear radiations, right? So this Variable Energy Cyclotron Center in Calcutta, which has got a cyclotron. There are medical cyclotrons also to produce that F18, what I mentioned, FDG. So these facilities support research in nuclear physics, material science, and other fields. Yeah, this is BRC, and the down picture that I had shown is a cyclotron, which is at Kolkata, that is Variable Energy Cyclotron Center. It conducts research in nuclear physics, accelerated technology, and material science. And RRCAT, it is called, it is an indoor. It focuses on advanced technology development, including lasers and accelerators. TAFR, again, it conducts research in nuclear physics, astrophysics, and material science. Saha Institute of Nuclear Physics. Then there is one in Hyderabad, Nuclear Fuel Complex, focuses on nuclear fuel development and fabrication. So these institutions contribute significantly to India's nuclear energy program, research and development. And there is one more facility. These are all national facilities which a simple university setup can't afford, because the accelerators that are there, those involve huge costs. Like say this IUAC, which stands for Inter University Accelerator Center in Delhi. Earlier it was called as NSC, Nabikiya Vignan Kendra. So this IUAC, it's a national user facility for accelerator-based research programs in India, which is on nuclear physics, material science, atomic physics, radiation biology, and accelerator mass spectrometry. It has got state-of-the-art facilities like this Pelletron accelerator and superconducting booster LINAC. Okay, and then some of these research areas at IUAC, those are in nuclear physics to study nuclear reaction, structure and decay, material science, radiation biology, and accelerator mass spectrometry. Okay, so I will stop here. Thank you. Thank you so much for the opportunity, and I'll now open for any questions.
Yeah, thank you very much for a very informative talk. You covered so many topics and so many applications of nuclear radiations. Now there is some time for some questions. If anybody would like to ask, they may raise a digital hand and then we'll ask. Let's start with the one already person, Dr. Shobha Devi. You can ask your question, please. You can unmute your microphone. It's muted. Okay, now you can ask.
Thank you very much, sir. Thank you, sir, Professor. Sir, very nice explanation. And regarding the PET scanning and the ordinary scanning, you said in the PET scanning they make use of cyclotron. And in the ordinary scanning, is it just a race? That is one question. And another, nowadays there is a interpretation of or interference of AI for scanning and treatment and all, detection and also curing. Can you please just explain this, sir?
Yeah, so let me make it clear. Cyclotron or accelerator facility is only to produce the isotope, radiopharmaceutical, that is required for PET. It is not used in PET. Right? The isotope radiopharmaceutical that is used in PET, mainly the FDG, fluorine 18, that is being produced by cyclotron. It's a medical cyclotron. So again, there is a disadvantage in the sense like you need to, for a PET facility in a medical setup, you need to have a cyclotron nearby which produces that kind of radiopharmaceutical, and then because the half-life, if you see, it is only 110 minutes, right? So less than 2 hours. So the activities that is produced in a cyclotron, it has to be very quickly, or high activity you need to produce to be transported to a PET facility, right? So those are some of the disadvantages. And then there is research that is going on. Actually, we also did some survey and research on any other radiopharmaceuticals which can give that kind of information as FDG or fluorine 18. Right. So fluorine 18, again, it has got its advantages, why it is being used as a PET tracer. So a cyclotron is not required, but to produce the radiopharmaceutical, it is required. And the AI part, to your second question, AI is basically all the medical background that you have, or medical images that you have. From that data, you can pick up and then say, or with more accuracy, without doing any scan, you'll be able to scan, or many tests, you'll be able to give a diagnosis. Actually, one more research that is done in our institution is called AMRX. With AI models, it can predict, say, urology disorders or some UTI related infections with more accuracy, without even pricking or pricking a patient, like without even blood sample, or just with their background, all this data, the AI can predict in a better, efficient way what kind of infection that you have. Yeah, I hope that answers it.
Thank you, sir. Thank you so much.
Srinivas Babu, would you like to ask a question?
Sir, my question is that you have told you are using a gamma camera.
Yes.
What is the sensor you are using in that, and what is the focusing element if it is a camera? Is it just like a X-ray film, or what are these elements you are using?
Okay, so yeah, there are some scintillation materials that I spoke about: sodium iodide, cesium iodide, lanthanum bromide, cadmium zinc telluride. These are some of the scintillation materials and semiconductor materials that are used as the detectors. Okay, so along with the detector material, there is again some electronics, like say photomultiplier tubes. Okay, so these collimators are also used. So with all this, you'll be able to, it's, when I say image, X-ray, you have seen an X-ray image, right? So similarly, this is the functionality of an organ can be made out from these images. So the focusing part, basically the collimator does. There are again different types of collimators. Different types of collimators and different materials of collimators. So there is research that is done on both materials as well, different materials, like say tungsten is one more material that is used as a collimator. So if you take a gamma source, it emits radiation in all the 4 pi directions. So it is not focused like laser. So to collimate it, you need some material which can say stream your gamma source or the energy. Right. So basically, the detector part, different materials are used, like say scintillation or semiconductor materials. The mechanism is different in scintillation, scintillators, and then semiconductors. In scintillations, like the most commonly used scintillator material is sodium iodide, but again, it has got its disadvantages. It is hygroscopic.
Okay, sir. Thank you.
Yes.
I have a few questions. You have covered so many topics. I'm sure there are a lot of questions from the audience. I have a few simple questions. You talked about radiation coming from banana. I mean, what kind of radiation have you detected at what level? What kind of radiation is coming?
It's something like it's some energy only that we talk about, right? So it is a beta emitter or say millisieverts that they talk about the dose. If you see,
What energy?
or even like say if you take a soil or a hilly terrain, the radiation that is emitted, it has got some kind of even actually banana it has got calcium 40 potassium 40 kind of radiation, that the energies that are coming from potassium 40, that kind of radiation that yeah.
You mentioned about this thing, crop mutation can lead to better quality of crops and all that. Can you give some examples? Are there any real working, seeds or whatever crops which have been used after processing by gamma radiation? Some example, concrete examples. Are they being used? Are they being used?
There are some centers that do this research, but I'm not
Because people are afraid of using radioactive seed.
really familiar with
They're
which are
worried.
the where crop mutation. Yeah, these are some of the applications, but there are centers which are working very
DRC,
uh,
DRC.
BRC has got, yeah, BRC has got this.
Any other questions? Dr. Nagaraj, you want to?
Yes, sir. You talked about the half-life. Any latest instrument is available to measure the half-life of any source? Let's say you said about 110 minutes, less than 2 hours.
Uh,
And how do you come to the conclusion, or what is the instrument you are using there?
yeah, so even a GM counter can
But
also
GM
measure.
counter long process, because even in our laboratory, I don't know whether what we are using a economy model in the laboratory, but there
No,
may be an
even
high-ended version of GM counter.
yeah.
But that's why I'm asking, is there any latest development in the instrument for measuring half-life?
Not necessary, sir. Even gamma Geiger counter also. See, if you know the initial radioactivity, uh, then the radioactivity at the time when it is produced, if you know that, then based on that you can calculate the lifetime, because it will be decaying, right? So at a later stage when you take a reading, the radiation that it emits, the counts that you detect, based on that you can see it has decayed this much. So in that way you can find what is the half life using Geiger counter itself. That is the basic instrument that is used for.
Okay, okay, okay. What I was thinking, whether there is any digital instrument so that directly we can find out the half-life. That's what I was thinking. I don't. That's why I asked.
uh, just for your knowledge, these manufacturers, say somebody like Artec, there is something called Oak Ridge Technical Electronic Corporation. It is US based. Indian also there are many. Most of the research work that is done at BRC, the technology transfer they do to some of the companies, and then they do. So for gamma spectroscopy or nuclear spectroscopic work, most of the semiconductor detectors and scintillation detectors, those are manufactured by this Artec that I mentioned, Artec, or now it is called Amatec or something. So and then Canberra Instruments. There are many manufacturers uh, who make these detectors, and then maybe I can share sometime a catalog of those
Any other?
where
Okay, we'll go on to other
Thank you, thank you.
questions. Okay.
I think any other person to ask some questions, clarifications,
Okay.
comments.
You can pass on the email of Dr. Vijay to anybody who is interested in asking further questions so that they can communicate with them, if you don't mind, so they can follow it up. So if there are no further questions, I request our General Secretary, Professor Nagaraj, to propose a vote of thanks.
Thank you, Dr. Vijay Sai, And of course, you have covered a lot of applications, exhaustive applications on medicine, agriculture, industry, even in research. And I was expecting something about aging also. Maybe I think anyway you didn't have time to cover about the aging, how actually the radioactive sources are used in finding out the aging. Anyway, you have covered lot of applications, especially in the medicinal field. So thank you very much. And of course, you have taken your time to give a talk in our platform. So thank you again. And we thank, we means Karnataka Physics Association is thanking all our life members and also the invitees. In addition to that, Karnataka Physics Association is thanking Dr. M.K. Raghavendra, who is providing this Zoom platform every Sunday. So we have to thank him. And of course, Dr. Kogli, and also Dr. K.S. Kiran, who has introduced you. You mentioned about Nanda also. I think he has introduced you to our association to give a talk. So thank one and all. Thank you again from APA to everyone who has attended this.
We also thank
Thank you. Thank you.
We also wish to thank S.V. Raman for providing the.
Oh, yeah, I forgot to mention that. S.V.
So,
Yes.
thank all the participants again, and thank the speaker for kindly sparing his time. I request all of you to join again next week at the same time for another talk. That is on 8th February. It should be very interesting. Thanks a lot. So now we are closing the meeting. Thanks to all of you. Okay, we'll end the meeting.
Thank you.
ఒక్క నిమిషం